Okay, today I will go on to do something on interference. That's a very, very important wave phenomena. Extremely important, extremely useful, and extremely applicable. And I'm going to show you after the lesson, if I have time, a few applications of it. Some of you may be actually wearing it on your way to school, that technology. Exactly, noise cancelling technology. Bosch, Sony bypass Bosch right now as the best noise cancelling company that offer the best noise cancelling headphone. So we'll talk more about that application later. So you need to know one thing, a couple of things before we talk about the application. So the first thing is diffraction. Now what is diffraction? Now gossipers, be careful. You have to know this phenomena because sound waves can diffract. Before you know it, you gossip about someone around the corner can hear you. Why? Why is it that light cannot diffract? Let's talk about this phenomenon. So what exactly is diffraction? If you have a wave coming in like this, it goes out like this. Okay? And if it comes in like this, it will do this. And then if it comes in like this, I'm intentionally not saying anything I'm intentionally not explaining anything. So it goes like this. It's almost like Chinese oral in primary school. So what do you make out of this? Okay, and then 如果波浪 Okay, this one diffraction happens, and this one diffraction happens. So what do you make out of it? Again, what's the difference between, actually I should close up this a little bit further. Yeah. What's the difference between this, and this? Yes, it has to be, no, the thing is that the wavelength gets bigger and bigger, yes. The wave front gets further and further apart, the wavelength gets longer and longer. So I want you to form a sentence in your mind. It goes like this. Diffraction happens when what? Form that statement. These three pictures. What's that statement? Diffraction forms when you can't draw straight lines. When you can't draw straight lines properly. Other than that, diffraction happens when something is comparable to something. Come on. You have to help me over here. What are those two somethings? When this is very much bigger than this, does diffraction happen? Very clear lah, diffraction happens. I didn't write anything here, right? So the answer is, diffraction doesn't happen. It goes right through. So what is diffraction? No diffraction, it goes right through. Diffraction happens. So what exactly is diffraction? Diffraction is a word starting with S. Spread out, exactly. It's the spreading of waves as it passes through an aperture or an opening. Yeah? And it only happens when this and this are a word starting with C. Comparable, yes, correct. Yeah, let's put this down. Let's put your inputs down. So diffraction is the spreading or bending of waves as it passes through an aperture or an opening. And it is very important for you to realize that if I call this D over here, when lambda is approximately equals to D or about the same order as D. So if you're talking about sound waves, what's a typical voice frequency? Boys or girls, roughly there. For girls, probably higher. For a guy, probably lower. Guess, what's the typical voice frequency for a person? About 2 kilohertz, about there, yeah. So 2 kilohertz, if you take the speed of sound, come on, tell me what's the speed of sound? 3 times 10 about 8? Sure, same. 330, yes, correct. About 330 meters per second. Yes, correct. If you take this divided by about 2000 hertz, that should be equals to about boom, boom, boom 1, this is going to be 16.5, so it's going to be 0.165, correct? About 16.5 centimeters, which means that if you open the door, the hole over here, the aperture over here is going to be comparable to about 16.5. It is not equal, but in the same order. And that's why when you gossip, the thing can go through and spread. Yeah, that's why people around the corner, they may be an eavesdropper down there. And then you're in trouble. Okay, so the thing is that's why sound waves can spread, and that's why sound waves can be heard around the corners. Because the wavelength is comparable to daily openings. Yeah? Okay? Now, why is it the light wave doesn't bend? Why can't you see round corners? By the way, it would be really weird if you can see round corners. How would the world look like if light were to diffract? How would the world look like? That means you can see round corners. It'd be really, really a weird world. But that said, then the whole world will be built around the idea that light waves can bend. Right? So to the people in that world, it may be normal. Because light waves bend. And they design the world according to that. Yeah? So, the reason why light waves don't bend is because the speed of light is 3 times 10 to the power 8, and the typical wave, the typical frequency is about 10 to the power of 15. So you're talking about the wavelength which is about 10 to the power minus 7 meters. Now there is no opening in the world that is 10 to the power minus 7, no matter how small your eyes are. Yeah, I don't think your eyes is going to be smaller, or any opening is going to be smaller than 10 to the power minus 7. But there is a way to actually show diffraction effect, and I'm going to show you now. If you can actually follow me, you take your thumb and your index finger, you try to find a light source, a bright light source, you put it very, very close. You might actually have to use the other hand to help you get close enough, and then put it up against the bright light source. When your thumb and your fingers are close enough, you actually start seeing lines, patterns, before your thumb and your fingers touch each other. You have to be patient. You have to be patient. If you bring it close enough, you can actually see vertical lines coming in. You can see, just before it touches. Okay, a challenge for people with psychomotor skills, but yeah. You can see lines just before it touches. I don't think you can capture it. Right. Can you see or not? You can see pattern coming in. So when your whole size, that whole size is small enough, comparable to the wavelength, these patterns, this weird wave phenomenon comes in. Okay? So as to why you see vertical lines, we'll explain it later in topic 9.4. Okay, 9.4. Why we see vertical lines. Cool? So, but for this one, this is about diffraction. And very important idea is that you have to have the wavelength comparable to the opening of the slits or the hole. Cool? Okay, let's go on to the next one. Why do we even talk about this? By the way, before I go on to the next part, you see, the thing is that about waves, it is perfectly normal. But how about if we send particles? If we send particles to it, if you send particles towards it, you expect particles sent to here, just go right through, right? Agree or not? But if you were to send electrons through this tiny little hole, if it is small enough, you actually see the pattern going like this. What do I mean? It means that if you've got a photographic plate, you should expect this part to be exposed. But what they realized is that they took the plate out, they studied the plate, a bigger area was exposed than what was supposed to be. So which means that electrons had diffracted. How does it happen? So what does it mean when the electrons diffract? Does it mean that electrons go through and then... Yeah, does it mean that? You know, one of the most interesting answers that you ask students at Sec 3 when you ask them what happens when an object is heated up, why does it expand? Then one of the most favorite and most amusing answers is that they'll say that the molecules expand. By the way, it's wrong, please. I look at the eyes of some of you and say, oops, I choose the answer. The molecules don't expand when it's heated up because it vibrates more violently. Yeah? Please, please. Yeah. So does it mean bigger electron or what? You think about this, Ken? You think about this. It's a very interesting phenomenon. When you send electrons one by one, they actually diffract as well. But what does it mean? If you're to be able to see an electron, how will it look like? That's the irony, right? When you want to see an electron, you need to throw photons at it. But when you throw photons at it, you actually change the way it behaves. So by observing it, you're actually changing the nature of it. Schrödinger cat, if you still remember. Okay, let's take a look at the reason why we talk about diffraction. Now, when you have a wave coming in like this, and it goes through these two areas, what will happen in the middle? The waves will overlap. Yeah, they'll overlap, and then they'll do this thing called superposed. Okay, superposed. That means that they add up. And there is a principle governing the way you superpose. It's called the principle of superposition. It states that when two waves of the same kind meet at a point, the resultant displacement is the vector sum of the displacement due to each wave independently. Looks scary, looks long, but actually what it tells you is very simple. And the only thing in your syllabus that you need to know is that when you add this and this, you get this. When you add this and this, you get this. Ta-da! Principle of superposition. How you wish you lived 200 years ago, right? Then for all you know, you might have a principle named after you. It's like, what? Yeah, this is principle of superposition. I mean, this is not principle of superposition, but this is where principle of superposition applied, it becomes like this. It's quite common sense, right? Yeah, it's quite common sense. It's very intuitive. So don't worry, it is a very easy to digest, it's a very digestible principle. But let's see, when you apply this to diffraction, waves diffracted, and overlap, what do you have? Okay, let's assume that you got two waves. Yes, Lauren, you seem to have difficulty reading my art piece. The last word? The last word. Line 1, 2, 3, 4. Line 4, first word. Oh, wait. I was asking last. Oh. She's asking this and you were asking this. Displacement independently. Oh. Yeah. Yeah. No worries, man. It's yeah, just get used to it. Like if you go to UK, some of the lessons are still conducted using whiteboard, of course. Our blackboard. Blackboard, actually. Surprise, surprise. And you got professors using chalk, yeah, to explain things. Right, let's take a look at what happens when you take one particular point, and that special point is the point where y minus x is equals to half a wavelength. Yeah, let's take a look. So what you have over here is, do you agree that waves from S1 will be the one that reaches the screen first? Make sense? Because it's shorter distance, so it should reach the screen first. Now, S2 is the wave that lags behind by half a wave. So what happens is, it will only touch the screen half a wave later. Make sense? Now, when you add this and this, what will happen? Which case is it? Left or right? Left or right? The right one, exactly. So you will have no wave. So this is what we call destructive interference. Destructive interference. The wave cancels out. So there's no wave over here. So if you happen to be in a concert hall, and if you happen to buy a ticket for a position where this is the point, then probably you'll be like, huh? But it doesn't happen in real life, right? It doesn't happen in real life. When you go to a concert where you have difficulty listening, think about why. Think about. There are two main reasons. Yes, the sound bounces off, so there are different paths it can take. And the other reason is, who goes to a concert to listen to a singer who sings only at one frequency? It's like for 2 hours you hear the singer singing, oh. It's like refund, refund, refund. Who listens to that, right? I mean, so you have changing frequencies, and therefore the path, this one changes because wavelength changes. So the condition constantly gets in and out of that condition. So this is destructive interference and no wave. And obviously, if you have destructive interference, we will have constructive interference, exactly. So let's go for another wave, another situation. And you will have this case, S1, S2. So let's consider the case where y minus x is equals to 1 wavelength. And then therefore you have the situations where this one reaches the screen 1 wave later. So they will add up constructively, giving you a very loud sound. Okay? So there'll be regions where it's going to be loud, regions where it's going to be soft. Now, why do I say regions and not region? Why do I say regions and not region? Because there are more than one positions where you can have constructive and destructive interference. How so? How so? Now take a look at this. Do you agree that this exactly the same thing will happen if I have 1.5 wavelength, 2.5 wavelength, and Agree? Now you have done mathematical induction. You should have inductive thinking abilities right now. So can you see that whenever the path difference, literally the difference in path, is equals to m plus half lambda, you will have destructive interference. Yeah? Where n is an integer. And then for this one, whenever you have path difference equals to n lambda, you will have constructive interference. Which means that if you add that and this is what you're going to see. S1, S2, and you will see loud, soft, loud, soft, loud, soft. Okay? Regions of loud and soft. Now, there are two things I want to go deeper. Two things. First, let's take a look. When you have constructive interference over here, if each of the wave produces amplitude A and intensity I, okay? And remembering that I is proportional to A squared. Now, when you have constructive interference, what's the amplitude of the wave over there? Sorry? 2A, exactly. So the resultant at this point, the resultant amplitude is going to be 2A, and therefore this is going to be intensity resultant is 2A squared, which is 4A squared. Therefore, do you agree with me that intensity resultant is 4 times the intensity? Which means that I have successfully violated conservation of energy. I got I, 4 I's. How? You got one person walking into the room, one person walking into the room, and then suddenly you got 4 people coming out. Okay, that sounds weird, but yeah, it sounds weird, but yeah, it's kind of weird. It doesn't happen, right? So yeah, it doesn't happen. Yep, it doesn't happen. So how so? I, 4I. Remember, I got intensity, each source, I and I. Now, you got this. How so? Now, you always, whenever you have problems like this in real life, one of the ways, like say for example, something that violates logic, probably you need to take a step back. Like say for example, people rushing to IKEA. It's like, what? Why IKEA? At that point of time, when it's a COVID issue, you're talking about what, meatballs? or furniture? But then it defies logic. But if you take a step back, right, why people rush to IKEA? Other than the meatballs part, lah. Yeah. Why people need furniture? Exactly. You don't, okay, I'm sure that every home will have furniture for studying, but not for the whole day. Right? Not for the whole day. Probably for 2 hours you lie on your sofa, you watch Netflix, okay. But not 8 hours when we ask you to report your link and then go for live lessons and then go for online quizzes and all these things. So you need furniture. So you need to take a step back and look at the whole situation as a whole. So this one, same thing. You take a step back, 4i looks weird, but other than 4i, there is something else. You have regions of 4i, you have regions of 0, exactly. So what's the average of 4i and 0? 2i, correct. So the one person walk in, then you suddenly got 4 people, it may be distributed from another class. Yeah? You only saw those 2 people walking, but it could be distribution of class. So the key word over here is that there's a redistribution of energy, not energy created. Understand? So sometimes you need to take a step back and check whether there's something you missed out in life. Cool? Can? Take a step back sometimes. It works. It may not work all the time. It works sometimes. That's the first thing. The second thing that we're going to reconcile is this. In real life, this is not what you expect. That always happens, right? Sec 3, your teacher teaches you F equals to MA, and then here, year 5, no, F equals to MA is not correct. I taught you this, and then just 2 minutes later, I tell you that this is not correct. At least I'm faster. You don't need to wait until 2 years later. So what I'm going to tell you is that this is never 0. The intensity at that point is never 0. Why? In fact, the intensity at the minimus gets higher and higher. So for the first 2 minimus, you might actually see this. The minimus gets higher and higher. Why? What is the assumption for it to be 0? For it to be 0, remember we talked about it's like this and like this. What is the assumption between these 2 waves? The amplitude the same, exactly. So is the amplitude the same? Obviously it is not. Because if the amplitude are the same, then it will be 0. So the question then, we take one step back, why is the amplitude not 0? I mean, why is the amplitude not the same? Remember, there are 2 conditions, there are 2 relationships you learn about intensity. One is I proportional to A square. What's the other one? Remember, I told you about the root 2, be careful, is x, that you move backwards. What's the relationship between I and distance? Come on, that was just less than 24 hours ago. 1 over r square. So ask yourself, is the distance traveled by the wave to the point on the screen the same? Is the distance traveled the same? This one and this one, the point that we talk about path difference means that they travel different distances to the point. Agree? If they had traveled different distances to the point, even if they began with the same amplitude, they will reach that point with different amplitudes. Because they travel different distances, therefore the intensity will be different, therefore the amplitudes will be different. Make sense? And the amplitude difference gets progressively higher and higher. Why? Because if I go from this point, the path difference at this point is half lambda. The path difference at this point will be, remember the different conditions back to here? 1.5 lambda, correct. So therefore the path difference over here is 1.5 lambda. Can you see that it gets progressively, the difference in distance gets progressively larger? And therefore the amplitudes gets progressively larger. And that's why the intensity gets higher and higher. Because you're talking about this wave trying to cancel out this wave. Different amplitudes. And that's why you will not get this. You will get something like this. Clear? Because of the path difference, probably let me map out this. Because of the path difference, it causes an intensity difference, it causes an amplitude difference. And that's why the destructive interference is not complete. Cool? So that's what you experience in real life. This is theoretical, it should be like this, but this is actual real life. And these are the higher order questions that I meant when I talk about the test. Yeah? It is not completely out of syllabus, but these are questions that stretches your thinking. Cool? So how do you apply this in real life? So what happens when you wear the noise cancelling earphone is this. It has a microphone that faces outwards. It has a microphone that faces outwards or downwards or whatever. It must have a microphone out. And then what it does is that it receives sound from the external environment, and then the electronics inside produces an opposite wave, which is this one. Yeah? And therefore, it cancels out the sound. You will notice something, that it can cancel out single frequency sound very well. Say for example, single frequency sound. Have you ever tried wearing the noise cancelling earphone on planes? It's a godsend. Seriously. I've never been able to sleep on planes for like the past 25 years. Until recently, I got myself a noise cancelling earphone that was a bliss. I could sleep 10 hours straight. Because of that, it really works very well. Because the rumbling of the plane, I don't think the frequency changes lah. If it changes drastically, pray already. yeah, correct. So it doesn't change, right? It always is going like this. There's a reason why it will change when it turns, but we'll discuss that separately. So it is very effective. But when you talk about voice, when you try to cancel out voice, it is very difficult for you to chase. Yeah, so it is very effective in single frequency. It is not that effective in fast frequency changing situation, because it has to catch up. The signal processing has to catch up, and it cannot catch up for very fast varying frequency. So that's one of the applications. In records, there is this technology invented by Head. I don't know whether you know this tennis brand called Head. Head, they actually put this chip inside the record, and it detects vibration from the play. And what it does is that it sends out a wave to a piezoelectric material that cancels out the vibration. And it's supposed to give you better control because of the cancelled vibration of the record. So these are applications in real life. But are vibrations all bad? No. There are people who actually try to get vibrations to generate energy. I went to NTU once, and they actually have this technology to try to get energy, because the blades in the fan, the blades in the wings actually vibrates a little bit. And they actually try to tap on that energy source, the vibrational energy. So not all vibrations are bad. Okay? So coming back to this, any questions you'd like to ask? Lauren, I thought I saw a question in your eyes. And you're going to ask something on... No. On something interesting.
It's about like waves and sound.
Yes.
What is resonance in the context of like?
Resonance. Resonance in the context of physics, basically, okay, let's park this aside. Resonance in terms of physics is basically you have an oscillating object, and then you push. Imagine you have a person who pushes the object, and if the frequency that you push the object is actually the same as the frequency of the object oscillating naturally, then it will reach maximum amplitude. Yep, so that's called resonance. It's just like if you think about metaphysical stuff, the communication is best done when you can connect, when you think alike. That's when you can transfer the thing better, the knowledge better. So resonance is basically about frequency. Yeah, and there is actually since you asked, it's a very good question, and I'm very tempted to show you more mathematically. Since you asked, you see. That's the point. I mean, you ask good questions, I'll give you even better answers. Remember power? Remember power? Looks like a lot of work needs to be done. No? What is this? This is Fv, right? Agree? Now, say for example, if you have a force that is oscillating force, yeah? Cosine omega 1t. Yeah, okay. Then you'll have an oscillating object where the velocity is oscillating but at a different frequency. So when you multiply these two together, you have F naught V naught cosine omega 1 omega t. Omega 1t, omega 2t. Still okay? Still alive, huh? Okay, good. So then can you see that this is F naught V naught? It is equals to half of cosine omega 1 minus omega 2t. Omega 1 minus omega 2t, and then plus cosine of omega 1 minus plus omega 2 upon 2 t. So remember, cosine A plus cosine B gives you cosine A plus B divided by 2, those things, yeah? The trigo identity. Now, what happened is when your omega 1 equals to omega 2, that means the force frequency is the same as your oscillating body frequency. This goes to 0, which means that you get a real force, a real component, which is 1 plus a cosine function. Now, if you perform integration on this function, the average of this is always 0. Why? Because if you find the area under a cosine graph, this and this will always cancel out this. But you have a real function that averages out to non-zero, and therefore you have effective power transferred to the object. And that's why you get the amplitude growing, because you're doing positive work to the object. Yeah. Only when omega 1 equals to omega 2, the oscillating body's frequency is equal to the force frequency. That's resonance, because you're doing positive work. If it is not equal, it will always be a cosine, and cosine, when you average out, it will always be 0. Whatever you give in will be whatever that is given back to you. How does it give back to you? When the object is pushing you. That's when it gives back to you. Okay? So, simple explanation and a more complex mathematical explanation. Hope it answers your question. Can people have a good day and stay healthy and stay safe.